Hi everybody. Thank you very much to the organizers of the conference, and Mirko in particular, for inviting me to speak here today. And I'm going to talk to you a little bit about some work we've been doing on making what we call quantum material Josephson junctions. The idea is to put in between two superconductors particular quantum materials of choice to see how the quantum material's intrinsic properties can modify the superconductivity that gets, tunneled across. So this was one of the images that we made for one of the papers that we published on this, where we exhibited a superconducting diode effect. So while it does also look kind of cool, the idea of the image is that there's unpaired single slow electrons going one way and Cooper pairs going the other way. So it was superconducting in only one direction. So as an outline, since it's the AtoCube's 2D material conference, I'm going to remind everybody a little bit about quantum materials and broaden a little bit from just topological materials. Then I'm going to remind everybody a little bit about Josephson junctions. So that's the heterostructure I described earlier, the superconductor, not superconductor, superconductor sandwich. And why it's actually pretty important. So maybe for technological applications, like some of the instruments that maybe AtoCube will make. And finally, then I'm going to dive into the quantum material modulation we're doing. And in particular, out of all the many quantum materials that one might choose to do this, I'll explain why we chose a particular Kagome insulator, so what those words mean. And the one we used in particular was niobium-3 bromine 8 to achieve this Josephson diode effect. So quantum materials, let's just remember that there's a lot of different quantum phenomena, so they're not best classically described. They're best described with quantum mechanics. So it goes from strong correlated things to certain types of magnets to, of course, topological things like Dirac and Weil semimetals and topological insulators. So there's, a whole zoo. And this thing, there we go. I got to point it right at it. So there's a whole zoo of different types of quantum materials that one can choose to play with. We're going to choose particularly to play with superconductors and the materials that are on the border of topological or magnetic. So this is an example, tungsten telluride, of a 2D, important topological material. This is probably everybody's familiar with YBCO, a famous high TC superconductor, which is actually, despite there being this A atom here, it's actually quite exfoliatable, and you can get, few layers of it. Everybody, of course, we've talked a lot about the honeycomb net and graphene today, and the one that we're going to focus on in particular is the Kagome net. So you may notice the similarities, that there's a honeycomb net in the middle, but the Kagome net has these small triangles that are connected. So we'll dive into that a bit more, and why this is important. And in particular, the question for these types of materials is, in the competition between magnetism, topology, and correlation, which can all coexist depending on the elements you choose, who's the boss? Or where does the arrow point? In some combination between correlation and topology, what happens when all these balance really closely? What sort of interesting phases do you get? And of course, 2D ones are especially fun since we can exfoliate them and easily craft them into devices. So a word on that. Of course, everybody, I think, has seen the so-called dry transfer technique, where you basically use Scotch tape, pick up some layers of a flake, maybe put it down, pick up some layers of another flake, put it down on top of your first flake. Or nowadays, you can use tape to pick up a flake, to then pick up the next flake, and so on and so forth. It's a very nice approach because you can deterministically make or construct your heterostructure as you choose. Here's an example for comparison. You can also choose the flakes you use and try to choose flakes that you can have overlap in a particular region, but leaves you room to do something potentially interesting to the rest of the device. In this case, it's just simple contacts, and the actual pathway of the current is down into the page through this overlap region. But it's important to also watch out. We've done a bit of work in the last couple of years showing that actually this approach is not as robust as one might think. Particularly, one needs to watch out for residue, bad touching. Different materials are more rigid or more floppy than each other, and sometimes that results in them touching at only a corner and things like that. And particularly, HBN does not protect things nearly as well as everybody likes to think. In particular, here's an example of we purposely, of course, illustrated this with a very hygroscopic material, nickel iodide. So this is, in this dark triangle is the nickel iodide flake. This is the HBN flake on top of it. And just within 15 minutes of being outside the glove box, you can see it's degrading. And by the next day, there's a literal puddle underneath the HBN. So you really got to watch out for what you're interpreting when you do a lot of this type of device fab and then measurement. Okay, Josephson junctions. So just to remind everybody, in case they're not familiar, the Josephson junction is, like I said, a heterostructure of a superconductor, not superconductor, superconductor. And this not superconductor could be a normal metal, it could be an insulator, it could be a constriction, like a point contact. There's a lot of ways to make a weak link between the two superconductors. And it was Josephson's pioneering work back in the day that explained that you can have still superconductivity across the not superconducting barrier, basically from a constructive interference of the wave functions. So while in plane, this is something that can be created in a one-shot fabrication. If you are using highly insulating materials and your channel length can't easily be made very short, if you're lucky, you might be able to use a 2D material where you can peel off just a few layers and sandwich it in between other 2D superconductors, and now you can get your very short channel length and get your superconductivity to tunnel across your material of interest again. So these are the Josephson effects. In particular, we're going to look at the DC Josephson effect in a particular quantum material junction. So I promised to mention that it's important. Josephson junctions are important. All of these things are based on Josephson junctions, from certain dark matter experiments to oil speculation using very sensitive magnetometers. Of course, MRI is magnetic resonance imaging, but the basis for that are superconducting Josephson junctions. And of course, all the most popular quantum computers still today are based on superconducting Josephson junctions. That's the EJ and your various types of XMONs or whatever they're called. So Josephson junctions are still relevant and quite important. So again, we're going to try to put a quantum material with non-trivial properties in between the superconductors and make, a QMJJ. And we're going to stick in between something that hopefully has an interesting property. Now, there are many different types, so we spent much of the morning talking about topological materials, and that's this session. So I'm going to explain how we started from there, or started to try from there, and ended up actually in a slightly different regime. We ended up using a strongly correlated material, but on the other side of superconductivity, a strongly correlated insulator. And it looks to be a Mott Hubbard insulator, but I'll explain why the logic went from topology. And again, there's many other different types of quantum materials, many of which are available in 2D form today, and some of which are available particularly in this class of material, which I'll throw a table at the end, which is why I'm saying this structure type is kind of maybe a good home, a good place to start. So that class of material is again called kagome. So this is a picture of a Japanese basket weaving basket where the word comes from, kagome. I think it means in a basket eyes, if I've been taught that correctly. And you can see that we can replicate that in a solid state crystal really exactly. So that's why these materials are called kagome materials. This is an example of the AV3SB5 family. So this is the potassium variant. And you can see the red sublattice is a kagome net of vanadium, interspersed with antimony in the brown atoms, and the A site is the alkali or earth. So the important difference one might notice between the honeycomb and the kagome is that between the empty hexagons, there is this sort of hourglass or two triangles that are upside down touching each other. This connection makes this so-called trihexagonal tiling. In graphene, all of your atoms are 3 connected. In the kagome net, they're all 4 connected. Because of that, the unit cell of the kagome net has 3 atoms, whereas graphene had 2. So this results in a similar but importantly different band structure. You still got your Dirac point crossing at K, like you have seen many times earlier, And now you've also got this flat band from the third atom that doesn't, let's say, or its orbitals result in a non-bonding band that ends up really quite flat and introduces strong correlations. So in this one material class, you of course have the potential for your topology because this can be opened through various perturbations, and then you can end up with topological insulating and surface state sites. You've got strong correlations from the Van Hove singularity as well as from a flat band down here. And like I said, this can be made up of vanadium, cobalt, many other types of transition metals can be put into the Kagome net. I'll give, again, a table at the very end. So you can introduce magnetism on what maybe to the people who are familiar with it is a clearly frustrated lattice because it's triangularly derived. So you get the trifecta. You get correlation, topology, and magnetism in one structure class. So where did we go from here? Well, we particularly were interested in the trigonally distorted Kagome net. So not the perfect one, but one where, if you notice, one triangle of those two triangles is smaller than the other. This is on purpose because this breaks the same symmetry, basically of one of the lattice sites, the AB lattice site, that results in the gap opening at K. So the idea was, okay, we'll crack that Dirac point that demanded it to be a metal, and we'll get potentially interesting topological result out. Well, in particular, the material we chose to use was niobium-3, chlorine, or bromine, or iodine. There's 3 variants at the moment, 8. So it looks like this, beautiful layered structure. Your niobiums are the green atoms in here, your halides are the brown ones, stacks on each other. If you look down the lattice, there you go, you've got your perfect distorted Kagome net. So it seemed like the perfect starting point. And back in the day, originally, it was, after people had done a theoretical calculation on it, predicted to be a TI. So we're like, okay, there we go. But a little while later, it was also predicted maybe to be a modified version, an obstructed atomic insulator, with the iodine being predicted in particular to be trivial. But more recently, much closer analysis has said, no, this is actually the perfect Mott insulator. That gapping ends up having not the desired TI effect, but the strong correlations of the material is allowed to dominate once the metallic behavior is cracked by the symmetry breaking, and it ends up going the opposite direction, being a strongly correlated insulator. So this was recent by a friend of ours, Malte Rosner, over in Nijmegen. But since I'm here in Germany, for the German audience, we also found this paper from like 35-something years ago, or 30 years ago, where if you read German, you can understand that they basically say that the experimentally determined semiconductor properties seem to arise from a Mott insulating state. And this was, again, 30 years prior. And particularly, this was derived from work with Roald Hoffmann, if you're familiar with that name. He won a Nobel Prize for various things in chemistry, but he spent a lot of time thinking about the Kagome net. So for the people old enough in the audience to recognize the meme related to the matrix, it's very much like deja vu, and things do sort of repeat themselves, even if they were forgotten for a while. So this is a more recent calculation on it by our friends Malte Rosner. And here you can see with his machinery the very nice band structure that results in the Mott state. So first off, formally, if you count electrons, you should have about 2 2/3 per niobium. This results in, with the charge disproportionation, of 7 electrons in the relevant orbitals. So if we simply count 2 electrons per band, you end up with filling your boring, let's call them, p orbitals, and end up with a half-filled band. The non-bonding flat band ends up being half-filled, and it should, in theory, have sat near the Fermi level, which, of course, is a very unstable state. And this is what they say pushes forward to the Mott insulating state. So this is basically how the theorists who I've talked to get about it, particularly Misha Katznelson, also, over in Nijmegen from the graphene fame. So basically, again, we have a flat band, it's half-filled, it's inside the gap, and in particular, although I don't have time to talk about it, the Hubbard U is far larger than the hopping. which is why they call this a deep Mott insulator. So it's a very exciting compound and family of compounds. But what did we do? We in particular said, okay, well, at the time we thought it was a TI, but fine, maybe it's Mott. Still, it's an interesting question of putting it in between two superconductors and asking what happens to the superconductivity across it. And so we made the usual type of heterostructure that everybody makes. We made a sandwich with HBN, our NBSE2 as our superconductor of choice, 3 layers in particular of niobium-3 bromine 8, although we did it also with 2 layers and with 4 layers and with 5 layers. But FYI, with 5 layers, we were too thick, and we couldn't get superconductivity to tunnel across the barrier. Right. So, yeah, we made this heterostructure and tunneled superconductivity across it. And so what did we see? Well, I'm going to go a little faster now since we're running a bit short on time, but if you look very closely, you find that the critical current to break superconductivity on the left side was different than the critical current to break superconductivity on the right side, meaning there was an asymmetry in the IV curves. And in particular, you could ask, well, what happens if I apply, let's say, a current in between these two values and just keep on flipping the polarity? And if you do that, you exactly find that you superconduct, then don't superconduct, then superconduct, and don't superconduct. So as a function of the direction you apply the same exact amount of current, you were either superconducting or not superconducting. This is very similar to a diode behavior, except it's a superconducting diode. So in particular, this happened without applying a magnetic field. So you can see if I look at the critical current in both directions as a function of applied field, you find that in just one direction, the critical current was always less than in the other direction up to a certain magnetic field. Now, this is very different from now there's many, many types of superconducting diodes and ways to achieve this effect. But this is still different than those types where you always have at b equals 0 or somewhere in the B curve a crossing of the two curves. So this mechanism is still not fully understood. And in particular, we also analyzed, of course, what happens if we remove the barrier. So do we just put NBSE2, twisted it on top of itself? You still see the X shape. What happens if you put graphene in between the NBSE2s? You still see the X shape. So this symmetric behavior versus, or what the non-intersecting behavior is still confusing and still something that people are trying to figure out today. So if you're a theorist, I invite you to take a look at that. But non-reciprocity in general, I just want to mention, again, for the particular audience, why it's important. So the diode behavior is maybe the most basic example of a non-reciprocal behavior, basically saying, again, that the signal doesn't travel in the same direction forwards and backwards. So the PN junction is, of course, one of the most famous example of a non-reciprocal behavior. But in general, non-reciprocity is important in a lot of circuit components, from gyrators to circulators and a lot more. From wireless computing or transmitting to quantum computing, we care about non-reciprocity. So making non-reciprocal superconductivity allows us to make some things in analogy to non-reciprocal semiconductivity. And this might result in dramatic reduction in energy cost for switching, might result in very high-speed switching as well. And of course, maybe with these quantum material approach, you might be very thin. So the brief overview of the field right now is that there are many ways that people have learned, including the old ways, to make superconducting diodes. In particular, without magnetic field, so far the quantum material Josephson junctions are the way to go. But what else is out there? We don't know. And there's been an explosion of realizations, particularly with the topological materials in the last 2 years. But basically, it's like it's been hiding in plain sight for the last 40, 50 years. We just didn't notice it. So the state of the art, since people always want to know, efficiencies are high. People can get up above liquid nitrogen now using those high TC superconductors. Switching speeds are still not demonstrated to be very high, and scalability has not been really demonstrated, but it's the progress of the field. So I'll leave this on while I take questions, but this is a table of some of these Kagome materials I was mentioning, and why hopefully you'll find them interesting. These are the 2 families I talked about today, highlighted in yellow, and you can read more in the review paper down here. So I'll stop here and thank you very much, and I'll come back to that slide. But thanks very much to the NWO for giving us lots of money, and in particular, Tyrell and Julia for their help and their materials. And Yaojie Wang and Hung Wu are the principal researchers of this work. Yaojie is now professor. So again, thank you very much.
We have time for one very quick question. We're seriously short of time. Is there a question? Okay. Yeah.
You can always talk to me afterwards.
Okay.
Since nobody's asking.
Okay.
It's also possible that this niobium-3 chooses to have a state where there's niobium 2+ and 3+ that are alternating. Is there an actual Mott transition in this thing?
Could you say the last part again?
So if there's an actual Mott insulator phase,
Yeah.
one might expect there's an actual Mott transition versus just a structural distortion, which gives you,
Right. Good, thank you. So there is, I didn't show it here, but there's a confusing transition at relatively high temperature that the material goes through, the various ones at different temperatures. But somewhere, for example, the chloride does it, I believe, somewhere around 200 Kelvin. And in magnetism, you can see the magnetism suddenly die. So people are still investigating if that subtle transition is related to a subtle further structural distortion that is really this Mott transition visible. But it'd be great to just dope it and move out of the band and see it. So if somebody's willing to work on that with us, we'd love to try that.